So letter A, did you get 69.5 degrees Fahrenheit? Good. All right, keep working. Okay, if you're having a little bit of trouble with B, this is a very interesting problem. I'm going to rewrite it as n minus 40 divided by 4. Okay, that's what that parenthesis means. So you could subtract 50, and then you would need to multiply both sides by 4, and you're going to get 4t minus 200 equals n minus 40, and then add the 40. So n equals 4t minus 160. Okay, do you see how to do that? There's your algebra. Subtract the 50, or you could multiply by 4 first. Just don't forget to multiply the 50 by the 4. All right, now it says use your function to calculate the number of chirps in a minute given the temperature is 20 degrees Fahrenheit. I'm hearing it whispered right now. That's somebody who's on the ball. We're getting negative 80, but what is n? What is n in the problem? The number of chirps. Can you have negative 80 chirps a minute? What does this mean?
The cricket is dead.
Yes, our cricket's dead. Okay, so I didn't mean to be quite so morbid on this one, but that makes sense, doesn't it? If it's 20 degrees Fahrenheit outside, that's below freezing. The cricket would be dead, wouldn't it? Okay, so apologize for being so dark on this one, but that's what's actually happening. So before I go on to our page that's going to be our regular notes, what I want to point out by these two examples is that when you have a word problem, and in this case we had temperature and number of chirps. If it solves for temperature and I want to do the inverse, I just solve it for n. Okay, in word problems, if you're trying to find the inverse, you just solve for the variable. You don't do anything else. So go ahead now and find your 1.7 notes. And what I want you to see, though, we're going to start off with a formal definition. The functions f and g are inverses of each other if and only if f of g of x is x and g of f of x is x. So it's a good thing we just covered composition of functions because we need that with inverses. So to show that you have inverses, you do the composition in both directions, and if it equals x, they are in fact inverses of each other. So in my first example, it says show f of x equals x plus 2, and g of x equals x minus 2 are inverses of each other. So what that means is we want to do f of g of x. So I'm going to replace g of x with x minus 2. And then you go to the f function, and it says input plus 2. Okay, input plus 2. My input is x minus 2, and then plus 2. Well, that's x. Then we're going to do the other direction, g of f of x. But f of x is x plus 2. So you go to g, and g says take the input minus 2. The input is x plus 2 minus 2. So f and g are inverses of each other because f of g of x equals x and g of f of x equals x. Okay? Alright, now, in my tool belt that I have, the tool I want to pull out is my light switch. And I did this last year, so this really isn't a new tool. What does this mean, and how does it relate to inverses? You switch, okay? You're going to switch your x and y, and then solve for new y. So let's write some steps down. So step 1, when you want to algebraically find an equation of the inverse, you switch x and y. Step 2, solve for new y. Step 3, new y is f inverse of x. Now I want you to think about our crickets, the temperature outside, and the number of chirps. In a word problem, you don't do this. In a word problem, you just solve for the other variable. These 3 steps are just algebraic, where you have an equation that has no context to it, okay? So, in this example, it says find the inverse of f of x equals 4x. So I'm going to switch x and y. So this becomes x equals 4y. Divide by 4. Y equals, and you can leave it as x over 4, or you can write that as 1/4 x. This is f inverse. And I hope you remember the notation from Algebra 2, that this is f inverse. And then it says, then verify that f of f inverse of x and f inverse of f of x are equal to x. So let's do that. We're going to do f of f inverse. F inverse of x is 1/4 x. So we go to f of x, and it says 4 times the input. Well, my input is 1/4 x. So that is, in fact, equal to x. Then we're going to do f inverse of f of x. F of x is 4x. And then it says take f inverse of 4x. Well, f inverse says take 1/4 the input, which is x. So this does verify that they're inverses of each other. Okay? All right, try the next example on your own. Do A and B. Find the inverse. So you're just going to switch x and y, and then solve for new y. That new y is f inverse. All right, letter A, I'm getting f inverse of x is 2x plus 5 over x. Why am I not allowed to cancel the x's? There's an x in the top and an x in the bottom. Why can't I cancel them? Sophia?
It's a term.
Good job. In the numerator, those are terms. You can only cancel common factors, not terms. So remember that from Algebra 2. Okay, so you switch x and y and solve for a new y. So what I did is I multiplied both sides by y minus 2 to get rid of the fraction. Okay? In letter B, you switch x and y, And then to undo a cube root, you're going to cube both sides, subtracting the 1. Oops. Yeah, okay, so now be careful. This is g, so g inverse is x cubed minus 1, okay? So to recap a moment, f of f inverse of x and f inverse of f of x, if both of those compositions equals x, you have verified that they are inverses of each other. Algebraically, you can switch x and y, solve for new y, and the new y is the inverse function. The next way to kind of look at inverses is graphically. Let's go ahead and put a grid on here. And for f of x equals 2x minus 3, I can plot this by going down to the y-intercept, which is negative 3, and go up 2, right 1, up 2, right 1, up 2, right 1. And then if you remember, when we say you switch the x and the y, that's actually true about your points as well. So if I look at f of x, that's 0, negative 3. So f inverse of x must have the point negative 3, 0. And if I have 1 comma negative 1, the inverse must be at negative 1 comma 1. Then I have 2 comma 1, so that's at 1 comma 2. And then I have 3 comma 3. So let me switch colors and plot these. Here's negative 3, 0, negative 1, 1, 1, 2, and 3, 3. And then what I want you to do is I want you to draw the line y equals x. And remember, the line y equals x is like 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and so on. Another way to look at an inverse is graphically. Graphically, if you reflect your graph across the line y equals x, that will produce the inverse for you, okay? Also, just switching x and y values will work, okay? So, algebraically, you can switch x and y and solve for new y. Graphically, you can either switch x and y and plot them, or reflect the graph over the line y equals x, okay? All right, now in the next example, f of x equals x squared. I created a table. And then what I did is I switched, and sorry, there's a little typo, if you guys can fix it if it's still not fixed on yours. I just switched the x and the y rows. So now the inverse is not a function because at x is 4, I have 2 different y values. And at x is 1, I have 2 different y values. So that inverse is not a function. So the big idea here, and again, this is all review for us, the horizontal line test is done to the original function. So if I look at this y equals x squared, okay, we know that's a parabola. If you draw the horizontal line through the original function and it's crossing more than once, what that's telling me is the inverse is not a function. But the confusing part might be that you're drawing the horizontal line through the original graph and it's telling you about its inverse, okay? So in the next example, I actually don't think we need our graphing calculators at all. x cubed, you know, looks like this, right? If I draw a horizontal line through it, isn't it going to pass the horizontal line test? So yes, the inverse is a function. And then what about x squared minus 1? Okay, it's a parabola and it's only been shifted down 1 unit. It's going to fail the horizontal line test. All right, I think you have some space here. And I want you to do one extra example, because this is in the homework and it will likely be a quiz problem. I want you to find the inverse of f of x equals x plus 5 divided by x minus 1. Okay, if you're getting started on this one, hopefully you at least got to this point, but then I can see you might get a little confused. Y is on more than one term. So what you want to do is we're going to subtract the y from both sides and add the x. If you could please, when you get one like this, move y on the left. Otherwise we're going to get two different looking answers. And then when you look in the back of the book, you might be like, wait, that doesn't look like mine. And usually you're just off by a negative sign then. Alright, so the goal here is we're trying to get the y alone. Any ideas? How could I get y alone? What, Tyler? You can factor it, right? That's one of our tools in our tool belt, is to factor it. So I can factor out the GCF, which is y. So I have y times the quantity x minus 1 equals x plus 5, and then divide both sides by x minus 1. So this is f inverse.
That's great.
Now wait a minute. That's the original problem. Okay, but normally they're not the same, right? Normally it's not the same. Let's go explore this. I want you to take out your graphing calculator, because you should go, why is that? So let's go, and I've already done it. Go to your Y screen and let's go enter the original graph, x plus 5 in a parenthesis divided by x minus 1. And then do zoom 6. Why do you think the function and the inverse are identical?
On these two graphs.
Yeah, okay, let's go back to the Y screen, and in Y sub 2, let's put y equals x in there, because don't we know graphically that if you reflect your function over the line y equals x, then it produces the inverse. And so Tyler's absolutely right. If you look at y equals x and you could fold your paper, the function maps right back onto itself, okay? And the inverse, so like, it just reflects right back and forth, okay? So that's why it was the same thing, okay? All right, does anybody need to see the equation again?